Okay, this is a video for Unit 11, Day 4. And just like normal, I want to start with a warm-up. So this is the warm-up that we would be doing in class today. And I would suggest you pausing the video for a second, writing down your answers on a separate sheet of paper somewhere. And when you think you're ready to see the answers, hit play again, and then I will talk you through it. So go ahead, hit pause right now. Okay, so I'm assuming if you're watching this section, you've already tried these. Part 1 says simplify each of the following exponential expressions. So remember, when I've got an exponent raised to another exponent, like 3 squared raised to the 4x, what do we do with those exponents? We multiply them. So 2 times 4x is 8x. So this is going to end up being 3 to the 8x. And similarly over here, don't forget you might have to distribute exponents also. So this is 4 raised to the negative 3 plus 3x squared. The negative got distributed, that's why I changed to a positive there. I also want to review negative exponents because those are going to come up in the lesson today. It says rewrite each of the following without negative exponents. Do you remember negative exponents just mean to flip? So 3 to the negative third means I'd flip that and make it 1 over 3 to the third. And 3 to the third is 27, so the final answer would be 1 over 27. Similarly over here, if it's x to the negative first, it just becomes 1 over x to the first. Or you could just say 1 over x. Alright, so keep those ideas in mind as we go through the lesson today. Today's lesson is on your own paper, so if you have a spot in your notebook that you want to write this down on, I would get that out now. And I'm just going to move to a blank sheet here. Okay, and then once you've got a piece of paper that you're ready to write on, you can title this. This is Unit 11, Day 4. And this is called Solving Exponential Equations with Like Bases. Okay, so remember the last few days we've been talking about these new parent functions, and our parent function has been y equals b to the x. And with these functions we have variables in the exponent. So for example, I wanted to do 2 to the x equals 4, and I want to solve for x. Some of you could probably answer this just by looking at it. If 2 to the x has to equal 4, what does x have to be? Well, clearly, x is 2, because 2 squared is equal to 4. So you can kind of just guess and check like that with some of them, but obviously they're going to get trickier than that. So the big question is, what if it's not so easy? Sorry for the not so great handwriting here. So if it's not so easy, we have to find some other way to do this. So if I'm trying to do 2 to the x equals 4, we'll start with the easy one still. I'm going to list out some steps off to the right over here that you can take. And the first step is kind of the key step. The first step is rewrite each side using exponents so that they have the same base. write each side using exponents so that they have the same base. So for this particular example, I would say, okay, what's my common base? Well, between 2 and 4, I can write both of those with an exponent or with a base of 2. So the common base would be 2. And I'd rewrite those. So we'd have 2 to the x equals 2 squared. Okay, so second step. Set exponents equal. So you saw this in the last Common Core prep. If the bases are the same, the only way that's going to be true is if the exponents are equal. So if 2 to the x equals 2 to the something, then x has to equal 2. Now sometimes, when they're trickier, you'll see in a second, that will result in another equation. So my third step is solve resulting equation. In this case, there is no, that word says resulting, sorry. In this case, there is no resulting equation. X equals 2 is already solved, so that's our answer. That's pretty much it. Now, as with any equation, you can always solve graphically as well. So I don't have a calculator to pull up to show you, but you know the drill. If I've got 2 to the x equals 4, I'd throw this into y1, I'd throw this into y2, and then calc intersect. If you got a calculator, I would suggest trying this to make sure you can still do it. So exponential function 2 to the x, you should expect that to look like that. And y equals 4 would look like that. If you hit second calc intersect, you'll get this answer of 2, 4. 2 is the answer we were looking for, because remember when I solve something graphically, I'm always looking for x values. So their answer is x equals 2, just like I said it would be a second ago. So anytime you got an equation, remember solving it graphically is a good check for sure. Okay, I want to go on to another example. So here's example 2. Example 2 is 3 to the 2x plus 1 equals 9. So again, I need to figure out what my common base is. So I like to write off to the side, common base. And between 3 and 9, 3 and 9 can both be written as what? Now the common base is 3. Was anyone thinking 9? As a side note, common base is not 9, but that's a common mistake that people do. A lot of people think, oh, well, there's 9, and if I write 3 squared on this side, then that's 9. And then here they say, well, that's the same as equal to 9, because then this would just be 9 to the 2x plus 1 equals 9 to the first, except the exponents equal. 2x plus 1 equals 1. Solve that. We'd have 2x equals 0, so x equals 0. All that is totally wrong. And the reason why it's wrong is because you can't change the value. You can only rewrite it. So a second ago, when I made that 3 squared, 3 squared's changing it. It's not actually 3 anymore. 3 squared is 9. So you can't change the value, but you can rewrite them so they have the same value in a different way. So I'm just going to write can't change value. Can only rewrite. let's go back over here and actually solve this the correct way. Between 3 and 9, the common base is 3. So we're going to leave this side alone. This is still 3 to the 2x plus 1. But we're going to rewrite 9 as 3 squared. So now I haven't changed the value. 3 squared, 9, same thing, just writing it a different way. Once the bases are the same, I can set the exponents equal. So I would have 2x plus 1 equals 2. And now I can solve the resulting equation here. So subtract 1 gives you 2x equals 1. Divide by 2. We're going to get x equals 1/2. And of course, you could use your graphing calculator to check. And I encourage you to do that now. So GC, we're solving 3 to the 2x plus 1 equals 9. I'm putting this in y1, this in y2. If you zoom standard, you should see a graph that looks like this. And if you do second calc intersect, the intersection point would be 1/2, 9, meaning that x equals 1/2, because the x value is your answer. Okay, any questions yet? Okay. Let's go on to the next question. So example 3. 4 to the a equals 8 to the a plus 1. Okay, like before, our first step is to figure out what's our common base. This one's a little trickier. Between 4 and 8, I need to be able to rewrite both of those as some base to an exponent. Think about it for a second. What do you think the common base would be? If you said 2, you're correct. Now, a lot of you might be thinking 4, and that's tricky. It's not 4. Why is it not 4? Because 4 to what power would give you 8? Well, it's not an easy answer. It's not 4 to the second power. It's not 4 times 2, because 4 squared is 16. So 4 is not going to get you the common base that you need. However, if you do 2, then I can rewrite 4 as 2 squared, still to the a power out there. And I can rewrite 8 as 2 cubed, still to the a plus 1 power out here. Again, haven't changed the overall value. 2 squared is still 4, 2 cubed is still 8. This is why I did the warm-up. I need to distribute these exponents before I go any further. So don't forget that step. This is 2 to the 2a. Sorry, I keep hitting that button. 2 to the 2a equals 2 to the 3a plus 3. We're going to set these exponents equal. So that's going to look like 2a equals 3a plus 3. There I've got a resulting equation to solve here. So if I subtract the 3a, then I have negative a equals 3. And divide by negative 1, I'll end up with a equals negative 3. That's my answer. Now, if you try to check this one, it's going to look a little ugly. So if I did the whole graphing calculator check over here, oops. So if you do the graphing calculator check here, if you try to do the old y1, y2 route that we've been doing, where I do 4 to the a equals 8 to the a plus 1, throw that in y1, this in y2, give myself a little more room here, you'll get a picture that looks something like this. 4 to the a looks like this, but 8 to the a plus 1 doesn't look that much different. You can still find the intersection. It's a little bit harder to do. Comes out to be negative 3.015, something like that. So you still get that answer of negative 3, but as these start to get a little bit trickier, it might be a better idea to move everything and compare it to 0. So what I mean by that is I can say 8 to the a minus 8 to the a plus 1 equals 0. That's an equivalent equation. I can throw this in y1, this in y2. 0 is just the x-axis. So if I'm comparing to 0, then even though the graph looks kind of crazy, this one's not too bad. It looks something like that. All I have to do if I'm comparing to 0 is just look where is it hitting the x-axis. I can still do second calc intersect. It'll give me 3, 0, but there's that 3 that we knew our answer was. So again, it's just check, but that's a strategy you can use with any equation. If you have trouble finding the intersection point, you can always bring it all, set it equal to 0. Just look for where it crosses the x-axis. Okay. Again, if I'm going too fast, you can pause at any time. But here's the next example for you. Example 4. Example 4 is going to come in 3 parts. So here's part A of example 4. I want to do 3 plus 7 to the x minus 1 equals 10. So just looking at that, how does this look different from the last ones we've done? Well, there's this 3 plus, there's this 10. Just like with radical equations and other things we've done this year, we want to isolate this piece. So I'm going to say, as a note, isolate exponential first. So that means I need to get this 7 to the x plus 1 piece alone. So we'll subtract 3 from both sides. That'll give you 7 to the x minus 1 equals 7. And now this should be pretty easy. Obviously, what's our common base? Well, it's just 7. This is already 7 to the x minus 1. There's no exponent here, but what exponent is actually there? Should be saying 1, 7 to the first. So now set your exponents equal. X minus 1 equals 1. Add the 1 over, we end up with x equals 2. And I could check that if I want to, but I'm not going to spend time doing that right now. Okay, now what if I change this slightly and now ask you to find 7 or 3 plus 7 to the x minus 1. Instead of equaling 10, I'm going to have it equaling 3. Okay, so I still have to isolate the 7 to the x plus 1 piece, or x minus 1. So 7 to the x minus 1 equals 0 this time. But now what's the problem? We have to get a common base between 7 and 0. Well, what do you know about exponentials like 7 to the x or 7 to the x minus 1? Well, remember from that first day, 7 to the x has an asymptote. There's an asymptote at y equals 0. It's never going to reach 0. So I would just say never reaches 0. So this actually has no solution. If you tried to graph it, there'd be no intersection point. Okay, now let me change one more thing on this. And do 3 plus 7 to the x minus 1 equals 4. We're still going to isolate. So 7 to the x minus 1 equals 1. Now I need a common base between 7 and 1. Well, how can I get a common base with 1? Remember this fact. Recall. b to the 0 is always equal to 1. So that means whatever base I pick, if I raise it to the 0 power, it's going to be the same as 1. So I can use 7 as my common base still. I can make this 7 to the x minus 1 equals 7 to the 0. set your bases equal, or exponents equal, x minus 1 equals 0, solve it, and you get x equals 1. And we could check that, and you would also see that the answer works. Okay, so those are some special cases. Example 5, let me bring this to your attention because this is also an important one. 6 to the 2 minus x equals 1/36. Now up to this point, we've kind of had some baby examples. This is more Regents level now. There's a fraction, and people freak out when they see fractions. But remember, when exponents are involved, fractions aren't that bad. Fractions just means there's a negative exponent involved. Let's see how I did the other part of the warm-up. So fractions just means negative exponent. So if I could show you here, I'd be covering up this 1. I wouldn't even be looking at the 1. I'm just thinking 6 and 36. Between 6 and 36, what's my common base? Hopefully, you're able to figure out that the common base would be 6. So 6 can totally stay, 6 to the 2 minus x, no issue over there. Again, don't think of this 1 over, this fraction, just think of 36. How can I rewrite 36 with a base of 6? 6 squared. So this is equal to 6 squared. But now I do have to worry about the fact that it's a fraction. Instead of being 6 squared, if I want it to be 1 over 36, I'd have to make it 6 to the negative 2. So negative exponent because I've got a fraction. Once you figured that out, it's the same from here on out. We've got 2 minus x equals negative 2. If I subtract this 2 over with this 2, we'd have negative x equals negative 4, and we'll end up with x equals 4, and you could obviously check on the graphing calculator. Okay, almost done. Here's example 6. Okay, 125 to the x equals 1/25 to the 4 minus x. Now, if you think you're starting to understand it, maybe you want to pause right now, see if you can try this one on your own, and then hit play again when you're ready to see if you know what you're doing. So go ahead, try that. Okay, so if you've tried it, or if you want to just watch me do it, here's the answer. Common base. Now when I look at this, I first see, okay, I've got a fraction, so I know there's going to be a negative exponent involved. So ignore the fact that it's a fraction. Look at 125 and 25. What's the common base that I can rewrite both 125 and 25 as? Again, it's not 25 because 25 squared is already way more than 125. But I can write both of these with a base of 5. Okay, so 125, I'm going to put it in parentheses, is 5 cubed, still raised to the x, that's a 3. And 1/25, well, 25 would be 5 squared, and since it's a fraction, I'm going to make it a negative 2. So 5 to the negative 2, still raised to the 4 minus x power. Now remember, you have to distribute these exponents before you set them equal, otherwise there's no point of rewriting them. So that was something that I remember people messed up last year. This is 5 to the 3x equals 5 to the, distribute that negative, it's negative 8 plus 2x. We've got common bases now, so we can set the exponents equal. 3x equals negative 8 plus 2x. I'm going to subtract the 2x over to end up with x equals negative 8. And there's my answer. Okay. Well, I've just got one more for you, And then you can try the homework. Example 7. 3 to the x equals 5 to the x minus 1. We know we need a common base. So is there a common base between 3 and 5? Is there a way to write 3 and 5 as a base to an exponent? I can't think of a way to get 3 and 5 written with a common exponent, or a common base, and it's not easy. So we can't solve algebraically right now. Now there is a way to solve it algebraically, you just don't know it yet. It's coming in a couple weeks still. But I can still get an answer. So just because I can't solve it algebraically, how could I still get an answer? I could do graphically. And that's why it's important to be able to know how to do things graphically, because you've seen this year that there's some equations that you won't know how to solve, and you need to be able to think of y1, y2, calc intersect. Because you got to get an answer somehow. Okay, so now this is one of those ones that if you do y1, y2, it's going to look a little ugly. So I would suggest making this 3 to the x minus 5 to the x minus 1 equals 0. Plugging this into y1, this into y2, hit zoom standard, you'll see something that looks kind of crazy, something kind of like this. Since I had made it equal to 0, I'm looking for where it touches the x-axis. And if I do second calc intersect, you'll get that this is 3.15 ... comma 0. It's actually an irrational number. It's not a nice number. So best we could do is a rounded answer. We'll say it's about equal to 3.2. Okay, so that is it. So now you should be able to do the homework. The homework for this is a worksheet, and you can find the worksheet on my website. You can print it off if you have a printer available to you. If not, it would be a pretty easy one just to copy the questions down and do it on a separate sheet of paper. But give those a try. Remember, this is Unit 11, Day 4, so you can use your homework answer key to check, see if you're doing it right. If for some reason you don't have your answer key with you, there's an answer key available on the website. Also, look under Unit 11, Day 1, and you'll see it there. So give it a shot, and let me know if you got any questions. Good luck.